Okay, thank you. And thanks to the organizers for having invited me in this nice place I discovered. So I want to precise something just to avoid a bad rumor. Inviting me is not a prerequisite to for getting a slot in the program, so I'm clear. So this morning I'm a little bit anxious because I plan to do something. I try to comply with organizer requests and to make an introductory lecture and not a presentation of my research activity. I will evoke a few of what we do in Nice with my colleague and mention him, by the way, because I feel that at the end I will be too in a hurry. So my colleague in Nice, with whom I have developed this activity with microwave topology, one is here, is Geoffroy Aubry, and there is also Mathieu Bellec and Ulrich Kuhl, and a few but brilliant PhD students, Alberto Razo Lopez here, and Mastis Reisner, who is now in postdoc with a good fellow of our community, which is Frank Scheffel. And I would like also to mention and to acknowledge two colleagues in Paris, Gilles Montambeau, and one in Paris and one in Lyon, Gilles Montambeau and Pierre Delplace, who were my mentors in topology, in physics, topological physics. It starts 15 years ago with the graphene, and the little I know I owe to them, and the vastness of my ignorance is my own fault. So I will try to evoke at the end what we have did in the past with microwave, but the main part of my talk will be devoted to introduce the concepts behind this wave topology and topological photonics and topological insulator. And this concept is not very complicated, but sometimes it's hard not to be confused by different things. So the beginning is to be clear of what is topology. And topologists are very weird mathematicians, because for topologists, these two balls are strictly identical. And I encourage you to try to play a soccer game with a rugby ball. Good luck. But for topologies, there is no difference. And there is also no difference between these two objects. So this is why, tragically, the topologies drown very often. So it's dramatic. But at least the topologists acknowledge that these two families of objects are not the same. Oof. And why? Because what they define as equivalence in topology is that two objects are topologically equivalent if they can be continuously deformed into one another without creating or removing holes or ends. So you see, you can continuously go from the donut to the mug without removing the hole or without creating another one. So this is the definition of an equivalent, a topological equivalent class. And there is a well-known and famous theorem which makes a connection between the local detail of an object, its geometry. Kappa of S is what is called the Gaussian curvature. The Gaussian curvature is 1 over S squared for a sphere, and for an object is the inverse of the Gaussian curvature is the product of the minimum and maximum local curvature. And this theorem makes a connection between the detail, the geometry, the precise geometry of an object, and its topological, its global property, because in the right-hand side, this quantity, 2 times 1 minus g, g is an integer, and is called the genus of an object. And this number counts the number of all. So g equals 0 for a sphere or its continuous deformation, and 1 for a mug and a nice unicorn of this one. And what is important is that the genus is an invariant. So it's a number, it's an integer, so an integer cannot change continuously. So it means when you want to pass from this class, this topological class to this one, you have to create something violent to create a whole. And this is, in fact, a topological phase transition. And the topological phase transition is always something which cannot be driven continuously. You have something which change abruptly because it's driven by integer or sometimes half integer. And I just introduce another topological invariant which is built on this genus, which is called the Euler or Poincaré Euler characteristic. I will come back to it later. So this is the central theorem, and this central theorem relies on the integral of all the surface of an object. What happens if we integrate over a small portion? For example, here in a sphere, I integrate over a small a path, a closed path. And this is important because it introduces two important notions, parallel transport and holonomy. Holonomy, what it is, it's an angle. It's the angle accumulates if you try to translate a vector always parallel to itself, following a geodesic or a path on a curved space. If you're on a flat space, you can do what you want, whatever the form of the closed path. At the end of the path, two vectors coincide after one periodic path. But in curved space, it's not the case. If you see, I don't know how to mimic the curvature, but you have a vector, and once you are on the equator, translation, and you go back to the pole, and at the end you obtain an angle, and this angle is the integral of the curvature along the path, and it's called an holonomy. And maybe the name is new for you, but you know this angle because it's well known. It's exactly the angle measured by the rotation of the plane of oscillation of the Foucault's pendulum in Paris. It's around, this angle is around 270 degrees, depends only of the latitude of Paris. If the angle accumulated in 24 hours. And this angle, up to a factor 2 pi, is exactly the holonomy. So you can define only by topological reasoning this angle without invoking Coriolis force and these kind of things. And I will come back to this holonomy because you will see that it will play an important role in topological physics. And there is another interesting and funny, at least in the name, theorem, the Hairy-Ball theorem, which says that this Euler characteristic, Euler Poincaré characteristics counts, and this is a concept very important in topology, the concept of obstructions, and counts the obstruction to parallel transport of a tangent vector bundle on a base space. So this is also an important concept, the vector bundle. And why this name? Because it is due to this topological constraint that you have this very nice colleague on your head. So it can be another shape, but you cannot comb a hairy ball without creating singularities of this type. So more seriously, you have a base space, you have a vector field, and if you try to follow parallel transport on geodesics of this curved space, you see that in geometry where the Euler characteristic is not zero, you create the number of the Euler characteristic gives you the number of singularities or of vortices you obtain by attempting to comb this surface. And on the torus, where the gender of the torus 1 gender 1, so the Euler characteristic is 0, and you can comb torus without any problem. I'm not sure that we will all be happy to have a head in the form of the torus, just to avoid the colic, but and state in a more formal way this Hairy-Ball theorem states that there is no nowhere vanishing continuous tangent vector field on an even dimensional in sphere. So Just to be, it's a little bit more subtle. In fact, chi doesn't count exactly the number of singularities, but the number of charge, of topological charge. So it means that you can have only one singularities, but with a charge 2. And this is clearly stated in the Poincaré-Hopf theorem. Okay, but first origin of confusion, this theorem doesn't mean at all that the torus is topologically trivial, because there is different kind of topology. For concerning the tangent vector field, the torus is trivial, with no topological constraint. But there is another kind of obstructions where the sphere and the torus has a completely different role, and another kind of obstructions which will be very important for the following. And this belongs to the field of homotopy. So I don't want to enter into this vast domain. I just give you a flavor of what it is, what homotopy is. And the best way to define is to use loops on a surface. So the definition is that the genus of an object on a surface of genus G, there are 2G fundamental non-contractible loops. Wow. And so what is a non-contractible loop? So first try to define a contractible loop. So if I draw some closed path on this object, and a contractible loop is a closed path that can be continuously deformed to a single point. So clearly you see that all this trajectory here can be smoothly deformed and converge to one point. So on a sphere, clearly every loop can shrink to a point. So it means that all loops are contractible, and this is compatible with the fact that the genus is 0. And to say that in a more formal way, it means that the homotopy group of a sphere is 0. So the homotopy group is easy to read. This S2 is a sphere, and P1 means that we try to cover, to encircle, to catch the sphere with an object of dimension 1. So this tells you uniquely that a sphere cannot be catched by a loop. Okay. On the contrary, on the torus and its continuous deformation, you can have two families of loops which cannot be reduced to a point. There is this family around the hole, around the handle, and this one around the tube. Okay. And these two families are clearly non-contractible. You cannot shrink this trajectory because we have the hole in the middle. And these two families are labeled by two topological invariants called winding number. And this is easy to understand because a trajectory, whatever a trajectory, you can always decompose it into a number of round circles in this direction and in this direction. So you have two independent directions labeled by two topological invariants. So are you able now with this to guess what is the homotopy group of a torus? What is P1 of T2? You have two integers. You can run this loop in a direction and the other, and you have two numbers. So extra meat at the lunch? No, it's not motivate you. So it's Z times Z. So it's clear, simply says that to catch a torus with a line, you have two independent ways labeled by two topological invariants, two winding numbers. And I'm right. Unfortunately, just a side remark, P2 of S2 is not 0. What is P2 of S2? So how many are we able to cover a sphere by an object of dimension 2, another sphere? So is it possible to wrap a sphere? And the answer is yes. And you can wrap it many times. So you have an integer, and you can define a direction, so a sign. So it's easy. And this is important. I'm sure that you are not over the moon by discovering that one can wrap a sphere and that the homotopy group is Z. But this is very important for the following, because this is a very meaningful physical quantity which governs most of the transport in the topological system. But I will come back to this later. And this fact was at the heart of this of the work driven by these three theoretic condensed matter physicists, awarded by the Nobel Prize in 2016 for their theoretical discoveries of topological phase transition and topological phases of matter. More precisely, three main works were awarded. First, invoking Kosterlitz and Thouless. Concerns the Kosterlitz-Thouless phase transition, often called also Berezinski Kosterlitz-Thouless, BKT phase transition. It's a phase transition in 2D system at finite temperature, but without spontaneous symmetries breaking. So it means that it's a phase transition which doesn't enter into the classification à la Landau. Okay, and this is essentially the unbinding of vortices in a 2D system. And the other work, the one I will comment and describe in the following, is the integral quantum Hall effects, and developed by Thouless. The K is not Kosterlitz. I will give the name in a few slides. And Alden, this is quantum Hall effect integral. You will understand why. So it's a system with broken time reversal symmetry due to the presence of a magnetic field. And Alden, a few years after, developed a new model without explicitly breaking of time reversal symmetry, and both provide topological analysis of the whole conductivity. And there is a third works that I was not aware of, and I have to thank Jan-Noël Fuchs to draw my attention to this. I don't understand anything about this work, so I just put the name, and you can search the reference. Okay, so this is my outline. So in the following 4 hours, I will cover all this topic. So no, my objective is to cover the first 3 points, and we will see which one I will have the time to describe between 4 and 5. This is two results we have obtained in my group. For the last is the recent results. This one is not recent, but it's also interesting. So we will see. Okay, so start with a journey between starting from quantum Hall effect and to topological photonics. So the beginning of the story is the quantum Hall effect. So quantum Hall effects, we learn how it works in elementary school, almost. So it's a 2D conductor connected, and with a magnetic field in this direction. And due to the presence of the magnetic field, there is a curved trajectory and an accumulation of charge carrier in one side, a depletion in another side. So at the end, what you obtain, and in addition to the longitudinal transports and to the longitudinal resistance, which can be written in this way, with the mass, the charge, the density of charge carrier, and though it's a phenomenological characteristic time when you wrote the conductance in the Drude model, if it's a decay, a characteristic time of equilibrium, okay, of local equilibrium. So in addition to this local resistance, to this longitudinal resistance, appears a transverse resistance or a transverse conductivity, because due to this accumulation of charge, you have a potential, and a potential proportional to the current in the x direction. And this transverse resistance, called the Hall resistance, grows linearly with B, as obtained here by, it is a historic curve obtained by Hall at the end of the 19th century, with a resistance linearly growing with a magnetic field and a longitudinal resistance constant. This effect is extremely popular and used because it's a very easy way to measure density and sign of charge carriers, and it's a very simple way to detect small magnetic field through just a measurement of tension. So, and it's massively used in industry. You have 2 billion a year used in your phone, in your car, in your bike, everywhere to detect small variation of magnetic field is widely used. So this was the situation at the end of the 19th century and during a long part of the 20s. Up to 1980, when 3 guys, von Klitzin, Dordain, and Pieper in Grenoble, decide to measure this Hall effect, but at low temperature and using a very strong magnetic field. Okay. And what they observe is that, for low magnetic field, we have the classical behavior with a constant longitudinal resistance and a linearly growing transverse resistance. But at higher value of the magnetic field, the story is completely different, because a staircase appears for the transverse resistance, and maybe more surprisingly, there is region corresponding to the steps of the staircase. There is a region where the longitudinal resistance is 0. 0 resistance means a perfect conductor, and the material used was not absolutely not perfect, supposed to be a perfect conductor. And what Klitzin, Dordain, Pieper noticed is that this plateau appear a quantized value of an elementary resistance, now known to the name of Klitzin resistance. Klitzin was very happy to be awarded by the Nobel Prize for the. I don't know if somebody knows that. I don't know why the 2 others were completely withdrawn from this. I don't know. I have not found any information. And this was clearly they observed this phenomenon, but they were not able at this time to interpret it correctly. There is different attempts based on gauge invariance, and it was not completely satisfactory, because the essence of the effects is of other nature, I will comment. But this resistance is so robust, the position of this plateau are so robust, because it's not dependent of the specific material use, of this degree of purity. So it becomes a reference of resistance, and now is even a fundamental, as it is composed of fundamental constants, its value is exact. Previously, it was known with a relative uncertainty of 10 to the minus 10, but since the last reform of the international system of reference in 2019, or I don't know, 19, something like that, since RK was fixed to this value, okay. So it's a reference, and this is typically the shape. This is a few 10 of microns, 100 of microns. This is a typical shape of an old probe used to measure resistance in a very precise way. Okay, so as I told you, the promoter of this effect, the searcher who obtained this result, was not able to perfectly understand and analyze their results. And there is some weird and strange effect, because between this plateau, clearly we see a transition, but this transition are not, as surprise, is not driven by temperature. There is absolutely no other parameter in this story, and there is absolutely no change in symmetry between in the system between these plateaus. So, and this plus the fact that these plateaus are extremely robust was a sign that the deep nature of this plateau are topological. And it means that this number should be a topological invariant. And it is, and in fact I will show you that is the best way to understand this number is to have in mind in the appropriate space a kind of twist in the wave function. So it's a difference between all these plateaus, the number of twists change. So it means that you cannot pass from one to the other with a global deformation. It's impossible when you have a Möbius strip. You cannot obtain a regular strip or a strip with two bindings. And the number of this twist is called the Chern number. And I will show you that this twist is related to the wrapping of the sphere, and that's in a few slides. And the first to understand the topological nature of this transport phenomena was Toules, associated with the three other colleagues. And they wrote a famous paper when they show that why the whole conductance was quantized. And they wrote not the resistance but the conductivity, then wrote it in this form when you integrate over space and over the k vector. And these two quantity, I hope that at the end of my talk, you will be able to immediately recognize that it is a topological quantity and something which is related to the curvature of the space where the wave function lives. And this effect was substantiated just after, a few months after, by these three very important guys in condensed matter physics, Avron, Seiler, and Simon. And they show all this, this provide an integer, and why this integer is related to the homotopy of the problem, of the wave function. Okay. So to understand this, I need to make a small detour in what I call baryology. This is the physics developed by Berry in the 80s, and I will try to be concise. So imagine that you have a quantum system which depends on a set of external parameters. I don't know the name, and you can control this parameter in time. And you have an equation of this type with an Hamiltonian depending of the parameter and this problem. Note that is not an eigenvalue problem because the parameter define the change the Hamiltonian. So it's not exactly the same. And you ask the very basic question, what happens if I choose a path in the parameter space, if I choose a closed path in the parameter space? It means that after a time capital T, a period, you come back to the same value of the parameters. You obtain the same Hamiltonian, so the basic answer say, okay, the two wave vector can be different only by a phase. You know that in quantum physics, a phase is not really important. But take care to the fact that you have parameter-dependent Hamiltonian. So it means for two different values of the parameter, you can have an overlap of the wave function. They are not orthogonal because this is without with h not depending on lambda, this will be a delta. These two wave functions will be orthogonal, but not in this case. And this overlap is very important because if you follow an eigenvalue or a band adiabatically, if the loop is run adiabatically, you can follow this overlap, and this defines what is called the quantum geometry, because I will be only focused on the phase, but you can also be interested in the norm, and you use a tool which is called the quantum metric tensor, and there are very interesting things to do with it. But I just will focus on the phase. And because of this non-zero overlap, which can be written in this way for a small difference in the parameter lambda, you obtain something which is proportional to this quantity, which is simply this. And this quantity is one contribution to the phase, because there is one trivial contribution, which is called the dynamical phase. It's simply due to the fact that if you follow the eigenstates, the energy also evolves with time through the dependence of lambda, and you have something which is simply Et of E capital T of H bar, and this phase is trivial. But the other one, due to the circulation of all this path of this quantity built on this scalar product, it's a geometrical phase, and it is the famous Fabrice phase. So to summarize, we have defined this Fabrice phase and build about this quantity, defined in this way, what is called the Berry connection. So the Berry phase is the circulation of the Berry connection. And one can define another very, very important quantity, which is the Berry curvature, which is the curl of the Berry connection. And it can be written in this way, is a cross product of the gradient with respect to the parameter of the eigenstates. And of course, via Stokes theorem, the Berry phase can be expressed as the flux of this Berry curvature through a surface. And this is important to notice that, because the Berry connection is not Gaussian invariant. So it means that it's not physical observable, but the Berry curvature is not, it's very easy to show. The Berry curvature is Gaussian invariant, so it means that the Berry phase is unobservable. So it doesn't mean that this value is not always zero. And it was, during a lot of time, the guess of most of quantum physicists decided to say, but this kind of phase is inessential, and there is nothing important associated to it. But it's not true. And Simon was the first. It's funny because Simon commented the paper of Berry before this paper was published. And he tells yes, I put. So it shows that the geometrical phase factor, recently found by Berry, is precisely the holonomy in an emission lie bundle. So this Berry phase is exactly the same status as the holonomy I described before, the holonomy which is an angle which appears in a curved space. And here this is exactly the same thing, except that now the curved space is not an object, it's what it's called the bundle due to the Gaussian variance, I will describe it later, and due to the structure in phase space of the band structure. And little bit more precisely, the Berry phase is a parallel transport defect defined on a fiber space. I will explain. This is a sketchy way to represent this. You can imagine that the phase invariance of quantum theory, the U1 gauge invariance, can be represented like a line, which is called a fiber, over the space of parameters. And the Berry phase is simply the fact that when you follow a closed path, there is a discrepancy due to this Berry phase in this on the fiber. And you cannot, if the Berry phase is not zero, you cannot adjust these two values. And there is a complete analogy with another well-known phase, the Aharonov-Bohm phase. And when I prepared this talk, I discussed with Geoffroy. And first, I was supposed just to say there is an analogy with Aharonov-Bohm phase. And he told me, come on, you have to present what is Aharonov-Bohm phase. So, okay, yeah. So, Aharonov-Bohm effect and phase. This is something obtained in the middle of the 19th century. And 19th. And what it is you have an electron beam, you build an interferometer system, a Mach-Zehnder with electron, and in the middle of the path, you put a magnetic field, but in a very limited region of space. I have this sketch here, so you have a solenoid, you have even a shield around to be sure that the electron never penetrates the region of space, and it means that you have a magnetic field inside the solenoid, so a magnetic flux. And what Aharonov and Bohm show is that the interference pattern obtained when the two paths interfere can be controlled precisely by the value of the magnetic flux, even despite the fact that the electron never feel the magnetic field, because they never enter into a region where the magnetic field and the magnetic flux exist, because outside B equals strictly 0. And by the way, there is two. When I prepared this, I discovered that two other authors, Ehrenberg and Side, discovered the same effect before, but I don't know why. It's just to be honest. And what is observed is that the dephasing observed here at the position. Suppose you have an initial dephasing without any magnetic field. But the dephasing is proportional to the circulation of the vector potential and is something which is controlled with a magnetic field and which depends on the flux quantum, which is h over E. And this is how the dephasing is controlled. And this is very famous results in mesoscopic physics, and I translate what Gilles wrote in his lecture notes in mesoscopic physics. It was the very first proof of the role of the vector potential and to see its effects. And it was not obvious because the vector potential is not Gaussian invariant, so it was supposed not to be an observable. So it doesn't mean that the Gaussian variant is an observer, but it means that it can have effect of quantity which can be observed. And this is a topological results also, because in fact I wrote here the circulation of A, but take care to the fact that this domain is not simply convex due to the fact that there is this singularity here. So you cannot define a single path. This is probably why they put color in the left and right path, because you cannot have a single contour. You have force to define two contours, one on the left, one on the right, and this is by doing this that at the end you obtain some things which gives you B and the magnetic field. And this effect was observed in system, very pure system, in high vacuum. So okay, but it was also observed in dirty system where multiple scattering occurs for the electron, and this is why it's considered as the first manifestation of mesoscopic physics, because even in system, it's in the normal metal rings, you have the transport of two electrons in a gold wire at I don't know the temperature, but in a situation where the scattering mean-free path is smaller than the length of the two paths of the interferometer, and this oscillation with H over E value was observed in this system. Okay. Here I told you that this is exactly the same physics. Why? Because in fact the Berry connection plays exactly the same role as the vector potential. The vector potential in the Aharonov-Bohm effect was due to the magnetic flux, to a genuine magnetic field in a limited region, but here is due to the band structure. And this, as noted by Simon, this is directly related to the results, to the TKNN paper. And I have to introduce, to comment this, a few words about band theory and how topology enters into band theory. So I will be brief because I guess that you know all the things. So when a problem with a periodic potential, depending on Bravais lattice, you know that you can write the Schrödinger equation in a form when you isolate, we have a Bloch's phase and a periodic function with the same periodicity of the potential, or it is Rj, and you obtain bands of energy separated by gaps, and each bands are labeled by a band index. And you have to avoid, due to this phase, to avoid to multiply count the same eigenstates, you have to reduce the domain of radiation of the K vector to what is called Brillouin zone, and to the fourth Brillouin zone. And the topology of the Brillouin zone is whatever the shape of its shape. The topology is always the topology of a torus, because you have boundary condition as two extreme value. So either you have a square, so it's easy to see that you build a torus with boundary condition, but sometimes you can have an hexagon, so it's less obvious, but it's the topology of a torus. So a torus appears in the problem. Okay, interesting. So the Bloch Hamiltonian can be written in this way with this energy band, and what will be interesting is this eigenstates. I will describe it. But what we obtain a continuous family of Hamiltonian, and the parameter now is the pseudo wave vector K inside the first Brillouin zone. So it means that this Hamiltonian falls into the domain of baryology I will describe. So we are supposed to observe the emergence of Berry phase and all this kind of thing in band theory. And this effect was not noticed. The role of the eigenstates was disregarded during decades, and people in condensed matter were focused in the energy band, and the eigenstate was not a very interesting quantity. So we can draw this kind of comparison. So in baryology, we define a fiber which is equivalent to the phase invariance in electromagnetism. The Berry connection is the strict equivalent of the potential vector. The Berry curvature is the equivalence of the magnetic field. The Berry phase, which is a circulation of the Berry connection or the flux of the Berry curvature, is equivalent of the Aharonov-Bohm phase. And all these attributes are purely geometric, because Berry phase is a geometric phase, not topology. So the question is, where is topology in this situation? Let's recall the Gauss-Bonnet theorem. How you obtain something which is topologically interesting is by integrating something which states the local property over the whole surface of the object. But in this case, what is the whole object? The whole object is the Berry zone. So when you integrate this, the circulation or the flux of the Berry curvature over the whole Brillouin zone, you obtain an integer which depends on the band where we perform the integration, as this integer is a chain number. And what is the equivalence in electromagnetism of this chain number? If I draw with the integral of the magnetic field, it's also an integer, and it remains hypothetical. It's what we call the direct magnetic monopole. It has been predicted in the beginning of in 1931 by Dirac. I recommend you to read this paper. It's amazing. There is maybe 2 or 3 formula. All the rest of the paper is written, but I can guarantee that it's not written by artificial intelligent agent. It's authentic intelligence. It's amazing. And what Dirac proposed is that the Gauss theorem states that the magnetic flux over a closed surface is 0, because the rotational if you recall the Maxwell equation, the rotational of B is 0. And Dirac showed that this flux cannot be different as 0, but is always quantized, and quantized in terms of this quantum flux. And this number is supposed to be the charge of a Dirac magnetic monopole. It has never been observed, but it's interesting because it provides also an explanation of the quantization of the charge, which is not included in quantum field theory. You cannot explain why the charge of the particle are quantized. But it remains hypothetical, but the results, the theory is very nice. And also it solves another problem of Maxwell equation, because you have a dual symmetry of Maxwell equation. You know that when you change a referential, you can move from an electric field to a magnetic field. So if you wrote the Maxwell equation in a covariant form, you have something which is supposed to be symmetric, completely symmetric. It's called the dual symmetry. But when you wrote this, you see that something is missing. And what is missing is the Dirac monopole. So if the Dirac monopole exists, we reestablish the dual symmetry of the electromagnetism. And regarding obstruction, here there is also a problem of obstruction in this problem. This is what Dirac comments very accurately. There is the fact that there is no global gauge can be used. Gauge, I mean gauge choice for the potential vector to define this flux. And this is the reason why this integral appears. And here it is the same effect when on the Brillouin zone, there is some zone where you cannot, with singularities, and you cannot define a global block phase. So I will do the same, say the same thing, but in some different words. So the chain number comes the obstruction to parallel transport in a fiber space. So you have a base space, you have this U1 fiber, and when you try to cover this base space, you have something which blocks, which forbids to define a global block phase. And take care, it's a gauge bundle obstruction, not a tangent vector obstruction. I say that because sometimes people invoke the variable theorem to be confused about what is possible or not, but it's not the same topology. And this obstruction are counted by the chain number. It counts the twist in the band wave functions. And with the constraint that the sum of the chain number of all the band must be 0. I have no time to show you why it is the case, but trust me. And now we are able to define the topological equivalent class. In fact, if you have two gap block Hamiltonian, and they are topologically equivalent if they can be continuously deformed into one another without closing the gap. It's exactly the same definition, the same way to define the topological invariance as the topological equivalent of block Hamiltonian is inspired for the topological equivalence of objects, and is not creation or destruction of all, it's closing or opening a gap. And what happens is at the interface between two topologically non-equivalent insulators, the gap is forced to close because of this topological constraint, and at the interface appears what is called in condensed matter domain walls, and in these domain walls you appears perfectly conducted edge states. And the number of these conducted edge states is given by the difference of the chain number between the bands you want to coalesce. And so it means we can define topological insulator in this sketchy way. So suppose I have a topological insulator of the quantum Hall effect class, I mean with broken time reversal symmetry. And suppose it has two bands, okay, with two value of their number. As I told you, the sum must be 0, so maybe +1, -1, okay. And suppose that the lower band is filled, the upper band is empty, and you exert a force in this topology, in this piece of material. You can connect it to drain or just a force. It's not important. You have a force in the x direction. So what happens? You have a force, so you have a mean velocity induced in this system. So you have a current density, and how to calculate it? But I have to calculate the mean velocity. So the mean velocity is calculated by the averaging over the first Brillouin zone of the velocity. I would have said it's calculated by averaging the group velocity, but it would have been an error because this velocity is not only the group velocity. You have one term, which is what expected, the derivative of the energy, the band curvature gives you the group velocity, but there is another term which cannot be viewed uniquely on the band, and this another term is due, it appears when there is a curvature in the space, and as stated by the appearance of the Berry curvature. And there is another term in the VTS which is called the anomal velocity, which is a cross product of the Berry curvature and the force exerted. So it means that when you perform the average, what do you obtain? The first thing, its contribution is zero. Why? Because due to the periodic boundary condition of the Brillouin zone, you see that this term disappears, and also it is well known that a field band doesn't contribute to transport. It's not possible, there is no space to have transport. But this second term is not zero. It's not zero provided that the Berry curvature is not zero. And it induces a transverse conduction where the conductivity, the transverse conductivity, is exactly given by the value of the Chern number, because the integral of the Berry connection over the full, the Berry curvature over the full Brillouin zone gives you the Chern number. So it means that we have this transverse transport in the topological insulator. But a question emerges: what happens when you reach, because this is okay for an infinite system, but suppose at least that this is semi-infinite with one interface with a vacuum. The vacuum is topologically trivial, or with another insulator, but a trivial one. There is a problem, because if the Chern numbers are not the same, there is a topological obstruction. We'd say a topological border patch hole. We'd say no, you cannot transit from this place, this insulator to this one, because there is topological restriction to this. So it means that there is no other choice, because you cannot have an accumulation of charge at the interface. What happens? There is no other choice that for a state in the bulk to migrate in the upper band. So one state migrates to the upper band. If it migrates to the upper band, it means that it closes the gap, because you have states in the gap. So this is a condition to have a topological phase transition, because if you want to change the topological class of two insulators, you have to close the gap. It's the same thing if you want to change the topological phase of objects, you have to create or remove a hole, and here you have to close the gap. So you close the gap, but you close the gap with states that have a definite group velocity in the x direction. And you have, because the derivative is this kx, so you have d over dkx gives you a group velocity in the x direction. It means that appears at the interface, what is called the domain wall, states with a definite velocity in the x direction, and states which cannot be scattered in another state, but because there is no other states to be scattered in, because you are in the gap. So these states are perfectly conducted H states, without any possibility to be scattered. And in fact, I forgot to mention this, when the state go to the upper band, you know that this conductivity changes sign, so you have a detour here to avoid the accumulation of states at the interface. But with this transport along the interface. And this correspondence between the topology of bands, this is a bulk property, to perfectly conductive H states is a famous concept which is called the bulk edge correspondence. And the question is maybe, okay, but when in a finite system, what happens when this downward flux reach the other boundary, but exactly the same thing. You have another states which appear, edge states, in this edge, but with the opposite direction of propagation. Okay. I hope you don't forget that we start with the quantum Hall effect. So why this appeared in quantum Hall effect? How this appeared in quantum Hall? Because if you remember, we have a 2D piece of metal, so it means we have a 2D electron gas, and the 2D electron gas has a property that the density of state is uniform. Up to the Fermi level, you have homogeneous density of states. So an homogeneous density of states is not really well related to periodic and to band, to block band. Okay. So how the band appears? The band appears because due to the magnetic field. Because if I write the Hamiltonian in the Landau gauge, I obtain something which is very similar to a harmonic oscillator, but in Px and Py. So it means in a strong magnetic field, what you have quantized, you know, the trajectory of a charged particle on the magnetic field is curved. But if the magnetic field is strong enough, this trajectory can be closed, which is called the cyclotron orbits. And in fact, you have, if you close an orbit, semi-classically, you have to quantize it in a Bohr-Sommerfeld way. So you have quantization of this orbit. And you have this harmonic oscillator and appears, here I show you the sketch done by Gilles Montambeau. When the magnetic field is increased, you create this, Landau level, and this level can be viewed as succession of flat bands separated by gap. So it is how the bands appear. And there is something interesting to note, that the degeneracy of this band are highly degenerated, because the degenerescence is proportional to the surface of the conductor, of the insulator, sorry, and to the magnetic field. So it means when the field increases, the number of states in a Landau level increases. But the question is, where these states come? And this is here that the H states appear. Here, what I plot is the position of the Landau level in energy depending of the y direction. Okay, so here we see the two border of the extension, and due to the finiteness, to the width, finite width of the insulator, of the metallic metal, you have a curvature of the Landau level. And now we understand what happened if I fix the vector potential or the level with a static magnetic field. You see that you have no state in the middle, except if you are here, but you intercept two at the opposite interface, or 4 or 6 H states. And these H states, the number of these H states are given also by the chain number, because, as I told you, you have an interface, you close the gap, and you have a number of HH which is given by the chain number. And this was proven by Atsuger in this also well-known paper. And if we are interested in how these states propagates, you see that the group velocity of these H states are given by the curvature of the Landau level up to the H, and the variation of this Landau level with respect to y. So we see that we have a given number of H states in a given direction and in the opposite. So exactly what we expect. And I forgot to mention something, is that and now we see what happens when the magnetic field grows. We populate different Landau level, and we have this raise of the transverse conductance, resistance, and the peak are associated with the transition here when we the Fermi level pass through a Landau level. Okay. And last point. Last point, very important for us, is that all this story is very nice, but there is one ingredient which is very important, it's disorder. Without disorder, the Hall effect cannot occur in this way. And this is due to the fact that the Hamiltonian is not a pure Hamiltonian with a kinetic part and the potential vector. You have always a disordered potential, which is due to, for example, substitution in purities, which comes from the doping of the semiconductor. It's absolutely, it's not absolutely, it's extremely difficult to avoid defect and impurities in this kind of material. So it means that these very clean pictures of Landau level and nothing in the middle is not exactly the true situation. The true situation is this one. We have the Landau level, but perturbed by the impurities, so you have a disordered potential. So what happens? Imagine that I can control the Fermi, the Fermi level or the potential, the chemical potential. So when I am in this situation when I evolve all the fluctuation of the potential, so we are in a clear state where I have 3 H states. Okay, so I draw it sketchy here. The 3 H states, one propagated in one direction and the other in the other direction. And they are perfectly conducting because in a semi-classical way to represent the S stage, this constitutes this well-known, famous skipping orbit. I don't like too much this semi-classical representation, but it can help to understand something. But there is this cyclotron orbit, half of the cyclotron orbit, which bounce over the boundary. And while they are reflectionless, is that due to the magnetic field, you cannot have a scattering on an extension larger than the cyclotron orbit. So even if you have a scattering, as far as there is nothing, no other states in the vicinity, you have no solution to come back and to follow in the same direction. So in this situation, you have this number of H states which are well defined. But when the chemical potential change and reach this region, depending of the exact position, you have localized or extended H states. So what happens in this region here on a step on a plateau? Here you start to feel the disorder potential. So it means that some cyclotron orbits fill the potential valley and in fact evolves inside the valley. If I zoom into this trajectory, it's not the trajectory of an electron. It's the equipotential of the disorder potential, and you see a cyclotron trajectory orbiting around this equipotential. So in this situation, nothing changes and we stay on the plateau. Okay, we still have 3 perfect H states and some states localized inside. But when the valley becomes larger and larger, what happens is that one of the H states start to fill the bulk states, And there is, we start to blur a little bit the perfect plateau. So you have a ramp. The longitudinal state starts to emerge. And when in this second region, when this trajectory becomes larger and larger, you can have a backscattering of one edge state on one edge to the other. So it means you have the insulator become a finite, the perfect conductor becomes a finite conductor. So now the longitudinal resistance acquire a finite value, and the number of edge states is decreasing. And if the number of edge states is decreasing, as the quantization is 1 over n, you reach the upper state. So it's good to see that the disorder is always important, whatever the domain of physics. So, we are happy by that. And so to summarize, the quantum Hall effect is important by the fact that in system where, due to a magnetic field, time reversal symmetry is broken, you obtain perfectly conducting edge states, and this is and quantized conductance. There is another quantum Hall effect, which is called the spin Hall effect, and which is essentially two copies of quantum Hall effects, but one copy for one given value of the spin, 1/2, and one other copy for -1/2. And these two copies evolve independently, and you have an edge states which propagate in a direction fixed by the spin. So it means that you move from chiral edge states to helical edge states, because the helicity of the edge states are fixed. Okay, I will describe in a more precise way in a few slides the quantum spin Hall effect. There is also another quantum Hall effect. I won't discuss it at all. It's called the quantum anomalous Hall, and it can be observed in ferromagnetic materials, so without external magnetic field, but with internal magnetization. But okay, just to be precise, of the three types of integer quantum Hall effect, because there is also another type of quantum Hall, but I don't want to discuss this. So in these two formulae, quantum Hall and quantum spin Hall, what is interesting is this perfectly dissipationless edge states separated by a bulk. It is the difference between a 1D system. It's not 1D physics. Even if the edge states are limited to spatially limited to 1D, and it's a bulk property which is expressed at the boundary, which means that it's not two counter-propagating states in the same vicinity. You have two counter-propagating 2 or 4, depending on the spin, state propagating, but separated by an isolating bulk. And I'm going to skip this, otherwise this was supposed to draw you the complete panorama of physics and topology, but I'm pressed by the time. Just the fact that starting from this condensed matter physics, there is analogy with classical waves, and especially in optics, because we know how to create band with classical wave, acoustic, optics, by structuring the media of propagation. But I have no time. I like this because there is connection between all the concepts we have seen, but okay. And this is so important that some people claim that it's a new era of humankind. So after Homo sapiens, we have homotopy, and Duncan Alden is the perfect species of the new kind of human beings. Okay, so we can do the same things with classical wave, especially with electromagnetic and optical wave. And this was stated by the homotopy man Halden and Ragu in 2008, and follow very briefly after by the first experimental realization of this kind of H states in a system where the time-resource symmetry was explicitly broken using a ferrite. So you see in this in a microwave regime, the field able to avoid an obstacle and to pursue its propagation. And also the other types where the time-resource symmetry is preserved, mimicking the quantum spin Hall effect with the couple rings, and by adjusting the coupling and with using isolator, they were able to emulate a pseudo spin and to provide experience of the first experimental results on photonic spin Hall effect. How many times I have? Okay. And the property which is explored is always robust H channel, because on the trivially in trivial topologic photonic lattice, you can have H states, then since they are not protected, you can have a scattering in the reverse direction. So it's not interesting, but it's always the same. With time-reversal symmetry broken, you have chiral H state propagating always in the same direction. And with helical H state, with the equivalence of spin-orbit coupling, you can have two robust channels, one for each spin polarization. Okay, so I will very briefly describe the experiment we have developed in Nice in the microwave regime. So the main ingredient is there are different things. Let me be more rapid. So there are different important ingredients. This is a vector network analyzer which generate and measure microwaves from a few megahertz up to 20 or 60, depending your budget, gigahertz. And for a physicist, is a S matrix, because you have two ports and you can measure reflection and transmission in a given phase and in quadrature. So you have the complete and complex scattering matrix. And we have this object I will describe briefly after. It's a dielectric material which have resonator, and I can couple energy with this kind of antenna which excites the magnetic field in between two metallic plates. And with this kind of antenna, I excite only the magnetic field in the direction perpendicular to the plane of the two plates. And we have one antenna in the center of this big plate, and we can move above the lattice we create. And here, for example, is a very nice lattice of sunflower with a Fibonacci, the Fogel spiral. There is a Fibonacci number hidden inside, and we can create. We have almost no limitation about the pattern we can create. And a few words about this resonator. They are made with perlimpinpin powder. I'm not able to pronounce this weird name. So what is important is that the permittivity is very high. We use two types of resonator from 37 to 45, reasonably low loss. And for example, can measure with the reflection measurement. Here I drew 1 minus the reflection. We can work with a well-defined, with a small width resonance. And if I scan the field just above and we see what happened inside the resonator, we have what is expected in 2D, a Bessel function, a G0 inside, and a K0 Bessel function, which is essentially a decaying exponential. So it means that we have resonator with the energy stored into the resonator with the evanescent tail, and so it means that we can couple through these evanescent tails two of this resonator and two and more, and this is what we obtain with two, with an antisymmetric and a symmetric eigenstate, and you can perfectly describe this with a tie-bending model with the same bare frequency and a coupling. And this is all the coupling evolve with distance between the two resonators. And this is an exponential fit, but we can also superimpose the modulus square of the K0 wave function, but it's easier to use an exponential. Okay? And the typical decaying length is 3 millimeters. Okay? So it means that after 2 centimeters, the resonator are not coupled. So it is the only limitation we have. And we can play also with, this is the S mode, but we can play also with p orbitals, with a p mode. And in this case, you have 2 coupling, depending if the nodal lines are aligned, or which is a weak coupling, or are parallel. This is a strong coupling, so you can play with a more complex space, but I will be limited in the following to S mode. So we have, in a very simple way compared to what has been described yesterday, we have access to the local density of states and to the dose, and this is the density of states of a square lattice. And if we focus on a given frequency by collecting all the amplitude measured above all the resonator, we can obtain the intensity distribution or given eigenstates. And this is in reflection. In transmission, we can obtain the phase. So if you have the phase, we can have the time evolution, because everything is linear in this problem. So we can measure the evolution in time of a signal ejected at a given resonator. So you can mimic pulse spreading even if we perform all the experiments in the frequency domain. Okay, so we have played with this with a lot of situations, fractality in quasi-crystal, enhanced conduction by adding a PT symmetry. Okay, I have no time. Even Penrose lattice, this kind of thing, and we have collaborated with a lot of very good physicists and good friends, including the chairman, of course. And okay, so seriously, how many time I have? I mean, don't tell me that, because I'm able to speak 2 hours now. But,
at least 5 more minutes. It's okay.
5, okay. 5, okay, so I will just do this because it's not the most exciting experiment I have performed, but it's important because there is other concepts I have not yet introduced, which are important for if some of you want to go into topological photonics or topological wave in the future. So I will simply describe what can be done in a very famous lattice, the honeycomb lattice. And the honeycomb lattice is important because it's a prototype, it's the flagship of what is called the bipartite system, where we can describe all the physics with pseudo-spin 1/2. Okay, so the honeycomb lattice, it's a triangular or hexagonal lattice with 2 atoms per unit cell. So it means that you can write your block Hamiltonian in a 2x2 with a 2x2 matrix, because you have 2 independent
lattice, let's say A and B. So you can represent the space wave function in the block state by a spinor, one half, one of the A sublattice and one of the B. And this quantity F is easy to obtain. You have a coupling which is T, so you have, let's say, BA. You have one coupling inside the unit cell, so it's T. You have one coupling, BA, but with a lattice, with a site in the other unit cell. So it means that you have a Bravais vector to introduce. It is a block dephasing. And one other coupling with the A site with another unit cell. And in this case, it's the other Bravais lattice which compose the block phase. So it's easy to understand. The modulus of this quantity gives you the spectrum, which is represented here. And, okay, this is the propaganda for the graphene. I have no time. And we obtain this well-known relation dispersion with three important points. So we have maximum, which are parabolic. We have fixed saddle points at the M points in the ear, and you have these six famous, but only two are different, Dirac points where the two bands touch and where the dispersion relation is linear. So it means that in the vicinity of these K points, if you expand in the vicinity of the K point, you obtain a dispersion relation which is linear with a specific specific velocity, which is given for the graphene with a Fermi velocity, and which is 1/300 of the velocity of light. So this is why the graphene was excite a lot the physics community, because you have in the vicinity of this Dirac point an electric mobility which is tremendously higher that can be obtained with other semiconductor systems. And for fundamental physicists, it's amazing because you have a relativistic equation in a system which is very easy to obtain. And we have also, this is the density of state, symmetric with the Dirac point and the two Van Hove singularity, and between -3t and +3t. Okay. And this is interesting because it's a generic of a bipartite system. So when you have a bipartite system, you can write the Hamiltonian invoking the polymetries. So you can have a new parametrization of this solution invoking this vector H, and this vector I dissociate the norm. The norm gives the eigenvalues, but what is interesting is the eigenvectors, because they can be represented in the block sphere, and it means that the eigenstates of every bipartite system can be represented as points on the block sphere, and this is very interesting. And the question is how to is it possible to wrap the block sphere? So if I can calculate the Berry curvature in a bipartite system, and let me go precisely. And the expression of this of the Berry curvature can move from the derivative, the cross product of the derivative of the eigenvector to the derivative of this unit vector lying on the block sphere. So it means that you have a mapping of the chain number in the first Brillouin zone with this Berry connection defined with the eigenstate to this definition of the chain number only evoking points at the surface of the block sphere. And now the chain number takes another significance, is how we are able to wrap the Bloch sphere. And this is a source of confusion because the Brillouin zone, Jean Dalibard explains this very well in this Collège de France lecture. This is often confusion because the Brillouin zone is a torus. I know we have a sphere, but we see that it's not the same space. And there is a mapping specific to the bipartite system to the evolution of the eigenstates in the Brillouin zone, to the evolution of the position of a unit vector in the Bloch sphere. And another way to say that, the topological obstruction, which is important, lives in the phase structure of the eigenstates, not in the geometry of the torus itself. So it's not so surprising and so weird to move from a torus to a sphere because we change and we stick to the structure of the eigenstate. Okay, so with this, I'm going to zap. A question occurs because the famous bipartite system, which will be described by Vincent this afternoon, is the SSH chain, which is a dimerized chain, which is a 1D system. So the question is there non-trivial topology for a 1D Brillouin zone? And the answer is yes, and this answer has been formulated by also a famous condensed matter physicist, Joshua Zach. And he said that, okay, in 1D, we cannot expect something very interesting, except that we have periodic boundary condition. And with periodic boundary condition, we can exhibit a topology which is, of course, less rich than the full topology with chain number, but we have something which is related to the Berry phase because of this periodic boundary condition. And he thought that there is also a winding number, also a topological invariant in 1D for bipartite system, and this winding number counts the times you encircle the equator of the Bloch sphere. And it is important for what I'm going to describe now because in honeycomb lattice, due to symmetry constraint, there is no chain number. The chain number is equal to 0. So there is no fully developed topology, but you can have interesting quantity. Yes, and also this role of symmetry. I can go quickly because Vincent will also describe precisely the role of symmetries in this problem. So just to conclude, you can have very interesting things which happens in bipartite system and with honeycomb, but around the Dirac point. Because here you see that I drew the streamline of the phase of the eigenstates, and you see that around the Dirac points you have a circulation and in two opposite directions is with a plus charge, and here with an opposite sign. So around the Dirac points you have a Berry phase, and a Berry phase with two opposite sign. So in a strict, if you don't do nothing with honeycomb, you cannot expect something very interesting. But what can be done is to deform the lattice, to induce spatial anisotropy, for example, by exerting a uniform strain along one of the axial direction. And what happened in this case? You induce this beta parameter, which is the strength of the anisotropy, and the Dirac points can't move. So now we have the scenario where, by adding this anisotropy, you have a scenario when you enhance the anisotropy, the Dirac point moves up to a point where they merge because they have two opposite signs. And after they have merged, there is no other option to open a gap. And this is also a kind of topological phase transition due to the charge of the topological charge of the Dirac bond. And we perform this experiment with our microwave setup. And what we see is for the honeycomb lattice, we have, so for a finite system, the Dirac bond is a deep. We have a deep. At the transition, I go briefly, but at the transition, what happens? What happens is that the density of states move to the linear density of states to a square root. And the square root around 0 is above the linear. So it means that we have a refill of states near the Dirac point, and above the transition you have a gap. And I guess I have to conclude. So, okay, we have a gap, we have edge states, and we can also just show a picture by inducing an isotropic strain. We can also follow the Landau level above and generate pseudo-magnetic field, huge pseudo-magnetic field to generate pseudo-Landau level in this kind of system. But I need 1 hour more. So I will stop here. Thank you.